To tackle the ever-growing demand of energy consumption, the Electrochemical Energy Storage Laboratory of National Center for Photovoltaic Research and Education, under the guidance of Professor Sagar Mitra, is working on indigenous development of rechargeable lithium and sodium-ion battery. This prototyping laboratory is funded by Ministry of New and Renewable Energy. It is situated in the IIT Monash Research Academy building. I am Abhinanda Sengupta, a PhD research scholar working under the guidance of Professor Sagar Mitra. I will take you through the various facilities, the research, the prototyping activities that are being conducted in our group. Apart from the prototyping of the lithium-ion and sodium-ion battery, work is being carried out on various next-generation battery chemistries. This prototyping laboratory has a capacity of 4 kWh per day in the format of 10 to 14 amp-hour pouch cells and has a capacity of 1 kWh per day in the format of 2.5 to 2.8 amp-hour cylindrical cells. Now, my fellow mates will guide you through the entire process of fabrication.
I am Manoj Gautam. I am a 4th year PhD student in this lab. This lab generally works under the 10% relative humidity. We generally manufacture lithium-ion battery in total 4 steps, from electrode manufacturing, cell finishing and cell testing. The electrode manufacturing part starts from material procurement. So we grade the material for cathode and anode. Then we start the slurry mixing. The slurry mixing generally we do in 2 steps for cathode and anode separately, which we have 5 liter of maximum size. The next step after the slurry mixing is the filtration process, which is used to make the slurry uniform. This machine is the roll-to-roll coating machine, which has 2 parts. One is the header and the last one is the tail part. Here we put our filtered slurry on this header part, which we have 2 different type of current collector. One is the aluminum, second is the copper, and which is used for cathode and anode. So the slurry on that the current collector goes through this different temperature zones, which has a uniform heating at the different temperature gradient, and we collect our slurry the dried in the form of dried electrode at the tail part. This is the intermittent cutting machine, which is used to cut the dried rolls of the electrode of cathode and anode. This is the slitting machine, which is used to cut the electrodes in the format of 18650 cells. The next step is the calendaring process, for which we use this machine to maintain and adjust the porosity of electrodes. Okay, this is the cutting machine where we used our calendared electrode to cut in a desired shape of pouch. So this is the semi-automatic stacking machine, which is used to stack our dried electrodes in the form of pouch. We also have 2 semi-automatic winding machine. One is related with pouch, which is this one, and the second one is with cylindrical 18650 cell, which has the capacity of 2.5 to 3 ampere hour. The next step after the stacking process is the pouch forming machine, which is done by this machine. So the process is the cup molding process, where we make a different size of cavity for pouch cells.
I am Uday Sundar, project engineer working at NCPRE Battery Fabrication Lab under the guidance of Professor Sagar Mitra. In this part, I am going to give description about part of cell assembly process. In this process, one of the most crucial step is to find out the manufacturing defects in stacked and jelly roll electrodes by using short circuit tester. For further processing, we will take into such tools like ultrasonic welding machine, semi-automatic grooving, and the top cap welding and pre-sealing machine to fill up this cell assembly process. In this stage, the cells are put inside the glow box for electrolyte filling process, carried out in moisture and oxygen level below 1 ppm. The electrolyte is filling under the vacuum atmosphere by using help of high precision dosing needle, followed by cells taken out for the sealing. We will do that crimping and preheat sealing process to finish the cell assembly. After the final assembly process, the cells are carried away from the glow box and keep it in a vacuum oven at constant temperature for soaking. For further process, the cells are taken into inside this vault for formation cycling and testing. So behind this instrument have the capability of minimum current rate 0.1 ampere to maximum range of 20 amps with the voltage will be 20 volt to test our batteries in a safe stretch. Once done the formation cycling and the testing, we take our batteries for safety test by using the needle tester.
Hi, I am Akash Ahuja, a PhD research scholar of this lab, and I am going to take you through the demonstration of the products that we have developed and manufactured in this our lab. So our group has been successfully able to manufacture the pouch cells from 10 to 14 ampere hour capacity and cylindrical cells with 2.5 to 2.8 ampere hour of capacity. The capacity of a battery is defined by the amount of current that it can provide on a steady state for 1 hour. For example, this 10 ampere hour of battery can provide the 10 ampere current for around 1 hour, and for the products requiring lesser amount of current, this battery can go for longer periods of time. Here the chemistry utilized for the development of battery is lithium NMC as cathode versus graphite as anode. However, we are also working on the development of different new generation chemistries such as lithium NMC versus silicon carbon, lithium rich LMO versus graphite, and all solid state lithium ion batteries for future energy storage applications, which are regarded as second generation energy storage batteries with a energy density of 250 watt hour per kg or more. So further work is also being carried out in our lab along with the lithium ion batteries, which is lithium sulfur batteries. So here you can see a prototype with a capacity of around 1 ampere hour. In order to utilize these batteries with the products, it is important that the designated capacity of these battery is matched with the power requirement of the appliances that we are using. If you see in this case, we are utilizing these batteries to operate this TV and a portable electronics such as this fan with an LED lighting. In this case, the voltage requirement of this fan is around 6 volt that uses around 2 ampere of current. The power rating of this fan is around 12 watts. Therefore, we have connected the battery in series to increase the overall voltage of the required product. So similarly, we have connected the batteries together in series to operate this TV. We can also see that changing the speed of the fan or turning off the LED lighting does not have any significant impact. If we were to utilize these batteries for the purpose of running an electric vehicle, these batteries would be connected in series to increase the voltage and would be connected in parallel to increase the overall capacity of these batteries. So if we were to increase the energy density required, we are going to convert these batteries by connecting in different combinations and put them together in form of packs and modules that are utilized for the electric vehicles. The future of green energy is the development of an isolated residential systems with their independent renewable energy source and energy storage systems. Along with the lithium-ion battery chemistry, our group has also been working on the sodium-ion battery chemistry. Now, the sodium-ion battery research has been blooming as an indigenous solution, which is a great alternative to the lithium-ion battery chemistry for stationary storage energy application because of its several advantages such as sustainability, safety, and because of its redox chemistry, which is similar to the lithium-ion battery and very low cost. This dedicated group has been able to successfully demonstrate a sodium-ion battery pouch cell with a capacity of around 1 ampere hour and with a voltage of 3.2 to 3.4 volts, utilizing NVP as a cathode and hard carbon as an anode. Along with that, an air and moisture stabilized cathode are also under the development stage. The next stage is to scale up these battery chemistries to produce pouch and cylindrical cells with 2 to 2.5 ampere hour of capacity.
Hi, this is Prashit Datta. I'm the CTO and co-founder of Veria Batteries Private Limited. With 8 years of intense R&D at IIT Bombay, we have developed a patented technology of ultra-safe lithium-ion battery cell. The cell I'm holding in my hand is of 14 ampere hour. The specialty of these cells are dendrite-free. It eliminates fires that are caused due to dendritic shorts. At the same time, these cells offer similar energy density and cycle life as of tier 1 cells available in the market. With various ultra-safe lithium-ion battery cells, we have made a battery pack and powered an electric two-wheeler. You can see in this video, Professor Sagar Mitra is riding the electric scooty. This video was recorded while doing internal testing of our battery pack inside IIT Bombay. Veria Batteries, the startup from Battery Lab, is founded by myself. I'm a PhD from Battery Lab. Sunil Mehta, BTech from IIT Bombay, having 35 years of business experience, and Professor Sagar Mitra. This company is incubated at Sine and funded by HPCL and Sine IITB. Veria has crossed many milestones while coming to the stage and received many awards and recognitions. Viria Batteries was a finalist in National Startup Award 2020 and has been receiving recognition and support from DPIIT and Startup India. We are the winner of Academia Industry Training AIT Award 2018, AWSAR DST Award. We presented the lab prototype in front of Honorable Prime Minister Sri Narendra Modi ji on 2018. In 2019, we raised our seed funding. In the next year, Viria got selected for UNIDO FLCTT Accelerator 2020 and IIT Startup Accelerator 2021. Viria was a finalist in Entrepreneurship World Cup 2021 for India region, winner of Miles Challenge.
Viria Batteries, can we have you on the stage?
First runner-up of IPL League 2021 Challenge. We have recognized by Maharashtra Startup Week 2021. Recently, we got selected as top 18 startups by Fund Enable 2021.
The propulsion of this technology will facilitate and enhance India's economic growth, social innovations, skill development, and also employment opportunities. It will actually reduce country's trade deficit and its oil dependency as well. Thus, fostering and implementing this kind of technology will actually involve a high-class manufacturing infrastructure with the resources which are locally available in the Indian market. This work is geared up to make an impact. Thank you.